All right, guys, last week we started talking about expressions and algebraic expressions. We are continuing that learning today. So the first thing I want you to do is evaluate the given expressions. What does evaluate mean? Solve. So you are working out each of these problems and finding the answer. Got it? All right, you have 4 minutes. Go for it. Okay. For number 1, I am dividing a whole number by a fraction. What do I do first? Put the whole number over 1 and then keep change, flip. So 5 times 4, 1 times 3. My numerator is larger than my denominator, so I need to divide. How many times will 3 go into 20? 6, which is 18, so that leaves 2/3. Any questions?
Wait, I got 1/4.
Nope.
Wait, so wait, you change the denominator.
Right, because we need to buy fractions, you keep change flip. All right, number 2. Your first one goes inside the house because it's the winner. And the second one goes outside. So what do I do now? I have to make my outside decimal a whole number. So I move it once to the right, and that gives me 6. Then what am I doing with the inside decimal? Also only 1. So that gives me 2.4. Yes? Then I can bring my decimal up into my answer and divide. Can 6 go into 2? No. Can it go into 24?
Yes.
How many times? 4. So I get 4/10 as my answer. Any questions? All right. Number 3. What am I going to do? I add first. This is like order of operation. 14 plus 8. 22 over 2. 11. And number 4. 14 plus 8. What do I do when I'm adding fractions to the denominator? Say that again. It doesn't change. So my answer is again 11. What do you notice about questions 3 and 4? It's the same problem, just written differently using grouping. Yes? Any questions? Thank you. All right, turn the page. Some more. Well, you can start with some second hand up vocabulary.
Okay. For this sheet, now we're looking at the Johnson brothers. We got 4 different brothers. Jaden has a number of jerseys and a number of caps. Does it say how many he has? No. So mathematically, if I know there's a number there, but I don't know what it is, what do I use? A variable. So we'll use a variable X for the jerseys, the variable Y for the caps. That sound fair?
Yes.
Okay. So Jerome has twice as many jerseys as Jaden, but the same number of caps.
Quit talking and humming, guys.
Josh has 3 times as many jerseys and caps as Jaden. And then Jack has 4 times as many caps as Jaden, but no jersey. So you see the picture? Okay, so one thing we're going to do today is we're going to use what we're going to call algebra tiles. The ones we've got aren't technically real algebra tiles, but they will serve the purpose. So we've given you, each table has a stack of red, blue, green, and yellow tiles. For this exercise, we're going to use your blue and red ones, okay? And what we're going to say is the X tiles are going to represent the number of jerseys, and we're going to make those the blue tiles. So your blue tiles represent jerseys. The red tiles are going to do the Y tiles. So that's going to be the number of caps. So your Y tiles are going to be your red tiles. Okay, everybody tracking so far? So I'm going to get you started because we found out last class this is an issue. What you're going to do is you're going to use the tiles to model what each person has. So for Jaden, Jaden has a number. What does a number mean? How many is that? A variable, but how many? One. So how many does he have for the caps? One. So I mean, in front of me, I'm going to put for Jaden 1 red tile. That's my Y. How many blue tiles am I going to put down for Jaden? 1. And that's going to be my X. So to do the model with the algebra tiles, or just use the blue and red, when you draw them, you can add in the X and the Y. So now that we've established what Jaden has, all the rest of them, Jerome, Josh, and Jack, are based off of what Jaden has. So read what it says, and you should be able to now model and then write your models onto the paper. Everybody understand what we're doing? So one person at the table should be in control of the tiles and draw the model. The rest of you will be able to copy it on your sheet.
I don't understand.
So now, look at this. Jerome has twice as many jerseys. So how many blues?
2.
2. 1, twice 2, or twice 1 is 2. But the same number of caps. So how many reds?
1.
Okay. For Josh, Josh had 3 times as many jerseys and caps. So how many blues? 3. And how many reds? 3. Because it's both of them, right? It's jerseys and caps. For Jack, Jack had 4 times as many caps. Which color is caps? Red. That's the Y. So how many reds?
4.
But no jerseys. So how many blues? That makes sense? Any questions on how many of those were found? Okay, so our next ones are putting those together. How many of you were able to do 2 and 3? Raise your hand. Okay, so I'll give you guys a couple more minutes. Now that you've got all of that, 2 and 3 on your own. So now that you've done this, we have the algebra tiles. We model the total amount of jerseys and caps the Johnson brothers have. So that's all of them. So basically, if I pull all my tiles together, how many X tiles did I have? Back to blue. So I go back to the X's. I ended up with 6 of them. And how many jerseys? How many Y's? 9. That makes sense. You understand where those tiles came from then? Okay. So now that we've done all of that, can we now put it all together and write an algebraic expression to represent the total number of jerseys and caps? Now I'm going off this last model. How would I write that as an algebraic expression? David?
Put 8 Y's and then the ratio sign and then 9.
No, it's not a ratio, right? Remember, I'm finding my total, right? So what operation is going to give me a total? Because the ratio is division. Will division give me a total? No. Addition? So how many blues did I have?
6.
How do I write that? 6 plus X?
6 plus Y.
Guys, this is really important. How do I write this? Mathematically, how do I write this to represent it? How many X's do I have?
6.
How do I write that? Doesn't matter. It doesn't. So I could do Can I do that?
You get because it's not as fun as
More importantly, can I model that? You know how many sticks I'm adding together, Richard? Richard, this is gonna be really bad for you. You need to get rid of those so you can focus on what we're doing, okay? So I cannot write it that way, guys. Remember, we had a whole discussion on that. I have to have my coefficient first because I can't model this. I don't know how many sixes I'm adding together. So we cannot do that. So 6x, and then we said to put them together, I'm going to add, right? How many y's did I end up with? 9. Make sense?
Yeah.
So 6x plus 9y. Seriously, Richard, get rid of them. Okay, let's go to our next page. Okay, here's your math vocabulary terms. You have your vocabulary sheets now. So I believe that's starting at number 8. Like terms are 2 or more terms that have the same variable raised to the same power. The coefficients of like terms can be different. It's okay if they are different. So we're going to start by, we're not going to look at combining like terms, which is a review of the properties of arithmetic and algebra that helped us do that. So we're going to write an algebra, an addition expression that highlights the different tiles in the model. Then, if necessary, combine like terms and write the expression using as few terms as possible. So if the tiles are the same, we're going to call those like terms. We're going to put those together. So we don't have actual algebra tiles. We're just using red, blues, and greens. So we're going to make the x squared. These will be your red tiles. The x's are going to be your blue tiles. And the constants will be your, we'll use those as yellow tiles, okay? So you can use your tiles and try to put them together. We're going to do this for several exercises. We're going to go ahead and just use this parameters. And we want you to start putting them together. So what we're doing here, you're writing an addition expression that is going to show you what this model means. Everybody understand what we're doing?
Yes, sir.
Okay, you can do it. So first one should go to least, and it all laid out for us. Okay. First question: how many terms are in your expression? So we were supposed to write the expression first, right? What was the addition expression you guys came up with to show our model? Right? Do what? How do you say that? Second power. Little math term. 2x squared. 2x squared plus how many x's? Plus how many constants? 4. So when I write my expression off that model, this is what it looks like. Does that make sense for everyone? Okay. Now let's start analyzing this expression. How many terms are in the expression? 3 terms, right? So it doesn't say it, but what are the 3 terms? Squared, 3x, and 4. So those are the 3 terms. Make that? Terms, guys, are just the pieces of the expression. Now, how does this relate to the algebra tile? Guys, the answer's so easy. It's as easy as we think it is. When 3 categories: red, blue, yellow. And 3 terms. x squared, 3x, and 4. Everybody see that linkage? So really the term is just what color is it in there. What is the greatest exponent in the expression? Technically it's 2 is the greatest exponent because it's x squared. So 2 is the greatest exponent. And then, what is the coefficient of x in the expression? Three. Okay? 3 is the coefficient of x. And how does this relate to your model? Do I? No. How does that coefficient of 3 relate to my model? What you got? No. That's why we have 3 colors for the 3 terms. How do I see the coefficient of that?
The coefficient is 3 and then
3 blues. I told them the first one, we've only done 1 so far. So there are 3 blue tiles, that's where that coefficient of 3 comes in. That's why we want you to make sure you understand that difference between coefficients and terms. They're completely different concepts. Are you seeing that they're different concepts? Terms is my 3 colors. So I have 3 terms, the reds, the blues, the yellows. Those are my terms. Those are the pieces of my expression. Separately, I have a coefficient of 3 because in my x, there are 3 of them. So for the coefficient, it's just those blue tiles is the 3. So those 3s are coming from different places. Does that help you understand that difference between the coefficients and the terms? Because that's really the biggest reason why I have these manipulatives out, to help you guys really visualize what that difference is. Okay? So hopefully now you're starting to see that. Let's go to our next page. Now we're going to mix it up. Guys, do this model. So set out, we're only doing 2 colors, greens and blues. Set them out exactly like this. And I want you to write an addition expression just like the model is done. Okay? So you have to do exactly like the model shows for your first one. So set them out like the model is set up. Write your expression like the model is set up. We'll start doing some other stuff in a minute, but I want you guys to take a minute to start with what they've given. So our first one, we're writing the addition expression just like it is. So how did you write this one? You're supposed to write the expression for it just like it is. David?
2 times 2 to the second power times 3.
Do I need to write the 1? Remember, I said given. So always the coefficient there, but if it's a 1, I don't have to write it. That being said, you be wrong? No, I give her credit on that. Does she have to write the 1? No, it's a given. And if it's not there, it is a 1. Make sense? So you'd be right either way. It's easier to just write it as y squared. So, does everybody understand why this expression actually shows our model? Anybody not see why that one shows our model? Thank you for being honest. What part don't you see, Latte? You see, how many greens do you see? No, to start. 2, so that's 2x. Plus, I have how many blues? 1y squared. Then I have how many more greens? 3x. See it now? So, as that model was set up, this is what it looks like. Does everybody understand that this expression shows this model? Everybody okay? Give me a thumb up, thumb down. Okay, so almost y'all of you got it. Now we're going to take the next part, rearrange the tiles, combine all of the like ones. In other words, put the same colors together. Then tell me, how many terms does it have? And write the new expression. So I'll give you guys about 3 minutes to do this. You're going to rearrange all your tiles, put the same ones together, tell me how many terms you got, and then tell me, write the new expression based on your reorganization of the model. On this one, now that we put them all together, what did we get?
Got 5x.
Good. And?
3y squared.
Okay, I'm going to just change one thing, because just for mathematical reasoning, we normally start with our highest value and then go down. So when we write this, technically it should have been rewritten as 3y squared plus 5x. Okay, but I'm not going to, honestly, because I were a test, I would have taken the other answer, because additive commuter property addition, you get the same answer anyway. But if I have the choice in the option, normally I start at my highest exponent and go down. Okay, so now how many terms do we have now in our combined expression? 2 terms, what are they? 3y squared and 5x. Is everybody okay with that? Good. So we write the new algebraic expression. We actually already did that. That one's this one. So now, if I'm going to represent the algebraic expression 3x squared plus x plus 2 using algebra tiles and sketch your model. So now we're going to add one in. This is a totally different one. So for the red x squared, we'll use red. For the x's, we'll use blue. And for the constant, let's actually use the green tile. Okay? So go ahead and put that model together at your table. This one should have been relatively easy. So for my, first off, how many types of tiles are needed? 3 types. 3 types are needed. How many reds did you use? 3 reds. How many blues?
1.
Reds, not reeds. 1 blue. How many greens? 2 greens. Okay. How many terms did you have in this expression? 3 terms. What was my coefficient for the x? What was my coefficient for the x? 1. 1 coefficient for x. That wasn't in the questions. I'm just trying to point that, pound this point in, right? And that's because I only had 1 blue tile, right? Make sense, guys? Are you still starting to feel more comfortable with how these are coming together? Because now we're going to go back literally to our first lesson this year. So for all of our new students, sorry, but here's something you should have learned earlier, hopefully, and it's called distributive property. So what we're going to do, I'm going to do x and y, so 1 green and 1 blue, but I'm going to do 3 sets of those. Okay, so put together 3 sets of greens and blues, and then we'll go from there. I'll give you guys 30 seconds to get. Okay, so on this one, now what we've done, you have 3 sets of the x and y left. Everybody good on that? Okay, technically, if I break it out, how do I represent that 3? I would use 3 yellow ones, yes?
Yes.
So I add 3 yellow tiles to your stack. So you now have 3 yellow tiles beside 3 green tiles beside 3 red tiles. Okay? So here's the deal. What we end up doing is, because this 3 is on the outside, that 3 is on the outside, it's telling me how many of those groups I have, right?
Yes.
When I start to break those groups apart, that 3 constant goes to each of those. Make sense? So now you understand why it's now 3x and 3y? Because I've taken those 3 groups and I've broken them into 2 separate piles. So if I analyze the parts of the mathematical expressions of the work example, what do we see? Which expression, number 1 or number 2, shows a product of 2 factors? How many think number 1 shows a product of 2 factors? Raise your hand. Nobody? Good. How many think number 2 shows a product of 2 factors? Raise your hand. Okay, almost everybody did on the second one. What does product mean? Okay, the problem. Am I multiplying 3 times x plus y, or am I multiplying 3x and 3y? What am I doing with the 3x and 3y? Adding. Is that a product? No. So which one shows a product? First one. For all of you that said the second one, do you understand why that was wrong? Because the first one is actually showing addition, right? Yeah. Now, our second question, how many, so the answer to this one is 3 times the quantity of x plus y shows 2 products. How many terms are in my expression 3x plus 3y? 2 terms. What are the 2 terms? 3x and 3y. The number 3 is a coefficient in which expression? Expression 1 or expression 2? How many think it's a coefficient in expression 1? Raise your hand. How many think it's a coefficient in expression 2? Raise your hand. Good job. You got that one right. Because what does coefficient mean? It means it's being multiplied by a variable. So it's a very specific mathematical definition. Guys, I'm running into this a lot. A lot of you are not learning this vocabulary. If you don't understand the vocabulary, you're not going to be able to answer the question. I'm having a lot of discussions with my side on unit rate still. Now remember, unit rate means compared to what of something. If you don't understand that definition, you'll never answer a unit rate question because you don't know what it is. Same thing on coefficient. If you don't understand, coefficient is when I'm multiplying a number by a variable, that by definition. So this one is the 3x plus 3y. Okay, now we're going to give you guys a chance. We don't have enough tiles for you to do this one. Well, my side technically does, but Mr. Chan didn't hand out extras. So we're going to make the x terms are blue, quiet. The constant terms are red. So make a model. Oh, wow, we're down to 5 minutes left.
Yeah.
Quiet. I apologize. Time got away from me. I didn't realize you were so low. So rather than doing the whole model, we're just going to go ahead and do this. Remember, distributive property is just where I'm doing the arrows, right? So I'm taking the outside term, I'm distributing it to each of the others. So if I do 4 times 2x, how many 2x's do I end up having? I have 4 sets of 2x. So how many x's do I have? 4 sets of 2x. So how many x's do I have? I have 4 sets of 2x. So I have 8x. Then I have 4 sets of 1. How many do I have? Okay, our next one. I have 2 sets of x plus 3. So if I rewrite this, how many sets of x do I have? 2. How many sets of 3 do I have? 2 for a total of 6. So quick review, very quick review on distributive property. Distributive property, I'm taking that outside number and multiplying each of the inside terms by it. Okay, you're going to need that because let's go to your homework. You got to get it into the video. So go to 385. Guys, please be quiet. It's on the video. You need to get this for everybody. So a few things. Describe 3 different ways you can use distributive properties to rewrite expressions. So take a look around. There should be a lot of ways to do this. I'll give you a hint. They give you a few clues in your remember piece. Going through the problems. Number 1, Nelson's going overnight. He's in charge of bringing wood. He starts the fire with 6 logs and plans to add 3 logs for each hour the fire burns. So represent the number of logs as an algebraic expression. So you're going to need, algebraic expression means I need a variable. You want a variable for logs. Suppose the family decides to stay for 2 nights. Write the expression for the number of 2 nights. I'll give you a hint. You can use distributive property on that one. Guys, you should not be talking right now. Create a model. You're not going to have algebra tiles at home, so you just have to use a model based on what we've been doing. And then rewrite part C. So you're going to model what we did for the 2 nights, and then write the expression. Here, rewrite each expression using the fewest number of terms. What does that mean? Put together the pieces that you can. So if I have the same variable with it, I can put those together. Follow your order of operations. Just realize if it's outside the parentheses, I'm going to need to distribute it first. If it's an expression like this, where I have a grouping symbol like a division bar, I need to do my top part first, and then I'm going to divide. Okay? This one, even though it's got parentheses, it's all just being added and put together the same pieces. Second page. I can't believe you're not even have your homework out. I'm giving you all this help. Okay, we write each expression as a product of 2 factors. In other words, I want the coefficient to be 1. What that tells me is I'm going to have to take this number out. So basically, I'm dividing my constant by the coefficient, which gets a little more complex when it's a variable, but it's not that big of a deal, or with a fraction. Number 4, at the end of each school year, having cleaned out all the school supplies. He's giving you P is the number of pencils, and they've now given you a relationship between each of the other things. 4 times markers and pencils, 3 more highlighters than markers. So you're going to have the markers first. Twice as many pens as he has highlighters. So they all build on each other. Start with your P is pencils. All the rest will fall in together. Then they want you to break it down. So they're doing an expression for this one, then this one, then this one, and then all 3 of them. They're going to be putting them all together at the end. Make sense? Okay. Any questions on your homework? Okay, good luck.